The next example is example 9.3.3, which is an application problem. A small petroleum company owns two refineries. The first refinery costs 20,000 US dollar per day to operate, and it can produce 400 barrels of high-grade oil, 300 barrels of medium-grade oil, and 200 barrels of low-grade oil each day. So those are the three grade oil that the company can produce each day. The second refinery is newer and more modern. It costs 25,000 US dollars per day to operate, and it can produce 300 barrels of high-grade oil, 400 barrels of medium-grade oil, and 500 barrels of low-grade oil each day. So the company has orders totaling of 25,000 barrels of high-grade oil, 27,000 barrels of medium-grade oil, and 30,000 barrels of low-grade oil. How many days should it run each refinery to minimize its cost and still refine enough oil to meet its orders? So you see here that it's an application problem. A linear function to be minimized is not given. You have to get it yourself by reading the given information. Also, the constraints are not given as a linear equation or linear inequality. You have to write them yourself. But before we do so, we have to define the variables. In this case, we have two refineries. So I'm going to define two variables as S1 and S2. S1 represents the number of days that the first refinery is operated, and S2 represents the number of days that the second refinery is operated. Then the total cost, let's see, denote the total cost. So it's going to be given by 20,000 times S1, which is number of days that the first refinery is operated, plus 25,000 times x2. This is our objective function that we want to minimize. Now, with the given information on the constraints, we can have those three inequalities. The first inequality is the constraint of the high-grade oil, okay? And the second inequality is just the constraint of the medium-grade oil, okay? And the last one, or the third constraint, is the constraint on the low-grade oil. And we have to have non-negative constraint because number of days that the first refinery and the second refinery can operate must be non-negative. So out of the three constraints and also the objective function, we can write the augmented matrix corresponds to our minimization problem. And as usual, since we have two variables, the first column, we put all the coefficients of S1 in the first column. And the second column will contain all the coefficients of the S2 variable. So let's look at the first row. I got the elements in the first row by using the first constraint. The coefficient of S1 is 400, coefficient of S2 is 300, and the constant term appeared on the right hand side is 25,000. Same idea for the second row in my augmented matrix. Coefficient of S1 is 300, coefficient of S2 is 400, and the constant term is 27,000. To the third row, the constraint on the low-grade oil, 200 is the coefficient of S1, 500 is the coefficient of S2, 30,000 is the constant term on the right-hand side of the inequality. Now, out of the bottom row, you put down the coefficient of S1 and the coefficient of S2, 20,000 and 25,000 respectively. So this is the augmented matrix corresponds to the minimization problem. We're going to take the transpose of this matrix. And after we have taken the transpose of this matrix, we're going to have the augmented matrix that corresponds to the dual maximization problem. And then after that, we proceed by using the simplex method, okay? So the transpose of the matrix is this one, okay? I'm going to define three variables, okay? y1, y2, y3, all right? And over here, the objective function now appear in the last row out at the bottom row. So we're gonna say that with our dual maximization problem, the objective function z, okay, is going to be, we want to now maximize, no longer minimize. Okay, when we wanted to minimize, we use the variable w, or at that case we use capital C. Okay, my capital C consists of two variables, x1 and x2, but in this case we don't have a square matrix. After we have taken the transpose of the matrix, okay, our new objective function under the dual maximization problem, my new objective function consists of three variables, y1, y2, and y3. So we want to maximize z, which is 25,000 times y1 plus 27,000 times y2 and plus 30,000 times y3. Coefficient of y1 is from this spot of the bottom row. Coefficient of y2, 27,000 is from this spot, and 30,000 is the coefficient of y3. We want to maximize this z based on two constraints. Okay, so the first constraint is going to be 400 y1, 300 y2, 200 y3. Change the inequality sign. Previously, the constraint was with greater than or equal sign, but now it's going to flip the sign to be less than or equal, and the right hand side is 20,000. Same idea for the second row of your matrix, corresponds to the dual maximization problem. Coefficient of y1 is 300, coefficient of y2 is 400, and coefficient of y3 is 500, and the right hand side is 25,000. Okay, and we still have the non-negative constraints. That means all the variables y1, y2, y3 must be non-negative. Now we are ready to proceed with the simplex method. Okay, by seeing two constraints in our dual maximization problem, we know right away that we have to add two slack variables. So seeing those two constraints, it implies that we have to add two slack variables. So I'm going to name my slack variables as S1 and S2 as usual. And the reason that we add the slack variable is just to convert the inequality constraints to equal constraint. Okay, so by adding the slack variable S1 in the first constraint, I can change that inequality to the equal sign. Same idea, by adding the slack variable S2 in the second constraint to the left, I can change inequality sign to the equal sign. And then I have to maximize this objective function subject to the constraints. There are two constraints, okay? But you can also say that you have the non-negative constraint as the last inequality. We all know that by seeing this maximization problem, we can now start writing or having the initial tableau, but I have to take care of the objective function first. I'm going to do it before I move you guys to the next page, because in the next page I already put down the initial tableau. So out of your objective function, you're going to be moving other terms on right hand side to the left, and that means I have negative 25,000 y1 minus 27,000 y2 and minus 30,000 y3 plus z equals 0. So this is your objective function. I'm going to copy that and bring it over to the next page. Okay, because I put down the initial tableau for you guys already. You know how to have the initial tableau, okay? The first column, as usual, the first column is for the coefficients of our first variable, y1. Second column is for putting the coefficients of y2. And the third column for putting the coefficients of y3. There are two slack variables, so the next two columns are for putting the coefficient of S1 and S2. Next column is for the coefficient of Z, and the last column in your initial tableau is just the constant term B, okay? I have moved my objective function over here, okay? In the last row or the bottom row of your initial tableau, okay? You put the coefficients of y1, which is negative 25,000, coefficient of y2, this guy, put it right there, coefficient of y3, which is negative 30,000, okay? There are no slack variables in your objective function, that's why those two spots are 0. You have one z in your objective function, so you put 1 right over there. The right hand side is 0, so you put 0 in that spot. Now let's put down the slack variables. Okay, the slack variables, since we have two slack variables, then the non-basic variables are S1 and S2. You put them over here. S1 goes in the first row and S2 goes in the second row. I don't need this anymore. I'm going to delete that out because I put it in the bottom row of my tableau already. We have to get some space because we have to talk about the entering variable and also the departing variable. To get the entering variable out of our first step, we look at the bottom row and search for the most negative entry. So this is the most negative entry. I'm going to highlight that with green. That is the most negative entry. And that most negative entry falls into the column of y3. It means that my y3 is going to be the entering variable. Okay, y3 is the entering variable. I have to determine next my departing variable. And as usual, to determine the departing variable, we have to compute the ratios. There are two rows above the red line, so we have to compute two ratios and compare them. Let's go ahead and do it. We compute the ratios. So out of the first row, we divide B by that coefficient of y3. So 200,000 divided by 20, that gives me 100. Do the same thing for the second row. Divide 25,000 by 500. 25,000 divided by the coefficient of y3, the entering variable, which is 500. That's going to give me 50. Then I need to compare those two ratios and get the smallest non-negative ratio between 50 and 100. 50 is smaller and it is non-negative. So I'm going to highlight that. This is my smallest non-negative ratio. And that smallest non-negative ratio, I got it from the second row. So it means that my S2 is going to be the departing variable. So I'll put a note over here saying that S2 is departing. And this guy is going to be the pivot element. That is the pivot element. And you all know the next step, right? To make life easy, I'm going to try to get the leading one out of that pivot element. So I'm going to bring this matrix over to the next page and then divide the second row by 500 to get 1 over here. After I've got the 1 in that spot, in the pivot location, I can then use that leading one to get rid of 200 and negative 30,000 in that column. So just have the non-negative entry only in that spot. Everything else in that column must be 0. So I bring this matrix over to the next page, which is this guy. I divide the second row. Looks like I have a typo over here. I divide the second row by 500. By 500. So let's erase that. Divide the second row by 500 because I want a 1 in that spot. Okay. So let me highlight my pivot element, okay? By divide the second row by 500, I get 1 in that spot, okay? So it's a typo, okay? After I've got the leading one, I try to eliminate everything else in that column, okay? To get it off that 200, I perform R1 minus 200 R2. And to get it off that negative 30,000 in that third row, I perform R3 plus 30,000 R2. And this is the resulting matrix after I have performed those two row operations, okay? Everything else in that column have been eliminated, okay? I'm gonna put that as a bigger size so we can then discuss about updating the non-basic variables. So previously, if you look back to the previous step, we did nothing to the first row, so that S1 is still the non-basic variable. But S2 has departed already, and we enter it with the Y3. So Y3 is now the non-basic variable. Y3, and that remains S1, okay? And by seeing that we're still seeing the negative entries in our bottom row, it means that we haven't reached the maximum value of Z yet. So we have to proceed with our second step. So searching for the most negative entry of the bottom row, which is this guy. I'm gonna highlight that with green again. So that is the most negative entry. So if you want to label, so Y1, okay, that column contains all the coefficients of Y1. So your next entering variable is your Y1. So this is the entering variable. To determine the departing variable, we have to compute the ratios, okay? So out of the first row, we divide 10,000 by 2,800, okay, 280. Out of the second row, we divide 50 by 3/5. Okay, let's compute the ratios. Compute the ratios. So divide 10,000 with 280. I get 35.714. And then out of the second row, I divide 50 by 3/5. Divide 50 by 3/5, and I get 83.333 out. Compare between those two numbers. The smallest non-negative ratio is this guy. I'm gonna highlight with pink. This is the smallest non-negative ratio. And I got that smallest non-negative ratio from the first row. It means that my S1 is going to be departing. So I'm going to put a note saying that S1 is departing. Okay, and this guy is going to be our next pivot element. So pivot. So the next step is again to use Gaussian elimination. I'm going to try to get the constant one out of this spot, so I can do so by dividing the first row by 280 to get a leading one or constant one as the pivot element, and then get it off everything in that column or the column of Y1. So I'll move this matrix to the next page and perform Gaussian elimination. That looks exactly the same as this matrix. I'm gonna highlight my pivot element 280, okay? I divide first row by 280 just to create a leading one. I again highlight it with pink color. That is the pivot element. That is pivot. And after I've got the pivot element, I use it to get rid of everything in that column. So to get rid of 3/5, over here in this spot, I perform R2 minus 3/5 R1. And to get rid of negative 7,000 in the third row, I then perform R3 plus 7,000 R1. And this is the resulting matrix after I perform those two row operations. Okay, I'm going to bring this matrix and make it bigger, okay, in the next line. Okay, and don't forget to update your non-basic variables. Look back. Y3 was the non-basic variable. We did nothing to the second row, so we put y3. Okay, but S1 was departed already, and we enter with the variable y1 instead. So y1 is our non-basic variable. Now look through the bottom row. You no longer have negative entry anymore. Okay, it means that you have reached the maximum value of z, and the maximum value of z is 1,750,000. Okay, that is the maximum value of z. And it occurs when your y1 is 250 over 7 and your y3 is 200 over 7. What about y2? It means that y2 must be 0. And out of the two columns for the slack variables S1 and S2, you're going to get the value of S1 and S2 that gives you the minimum value of the cost. So you can label it also saying that this is the minimum cost. Minimum cost or minimum capital C, because we let C stands for the minimum cost. Okay, and that minimum cost occur when your S1 is 25 and S2 is 50. Okay, you have the minimum cost when S1. Do you remember what S1 stands for? S1 stands for number of days that the first refinery is operated. And that S2 is 50, which is number of days that the second refinery is operated. Okay, you get the minimum cost of that 1,750,000 US dollars. Okay, under S1 as 25 and S2 as 50. And we're done solving this minimization problem.